Let's review some concepts we learned from the last lesson. For example, one, many of our clothes are dyed with a weak base. We need to calculate the base dissociation constant given the initial concentration and the pH of the solution. Now, for this question, we're not given the identity of the weak base, but we can still use the general equation of a base reacting with water. Because we have the presence of a base, the water will by default act as the acid. The base will accept a proton from the water to form the conjugate acid to the base. And we, of course, form that hydroxide ion. When it comes to solutions with hydroxide ions, we can tell if it is basic or not. The greater concentration of hydroxide, the stronger the base, because it will favor the reaction to the right. It will favor this product. Um, because we need to solve for Kb, we know that we have to set up an ICE table as well as the Kb expression. So we have our ICE table where the only information that's given is the initial setting of the base, which is 0.1 mole per liter. So we're only given the concentration. We don't write anything for water because it is in its liquid state. We can assume that the concentrations of your products are zero at initially. We need to account for the change where all reactants disappear and your products form. We take the sum of the two rows to get the concentrations of each species at equilibrium. Let's set up our Kb expression, where Kb is equal to the product of the products, the concentration, and their corresponding coefficients as exponents, divided by all of your reactants in the same fashion. If we were to plug in the equilibrium terms, we would get x multiplied by x divided by 0.1 minus x. Now, at this point, we cannot actually solve for Kb because we have too many unknowns. We have x as well as Kb. So we kind of have to look back in the question and say, okay, we're at a standstill here. Is there anything else that's given? And at the last line over here, it gives us the pH of the solution of 11.8. We need to relate pH to the concentration of OH minus. So the way to get to that point is first we need to convert pH to POH. From POH, then we can find the concentration of hydroxide ions, just like how we relate pH to the concentration of hydronium ions in an acidic solution. So I'm going to write my solution up here to find the concentration of hydroxide so that we can input it into our expression. So for the first one, I'll just write number 1 here just to show you the steps. To get from pH to POH, we know that the relationship between these two variables is the sum of them will equal to 14, the highest value on your pH scale. We know that the pH is equal to 11.8, so we can determine that the POH is just subtracting 14 from the given pH value. So POH is equal to 2.2. The power of hydroxide ions is not the same as the concentration of hydroxide ions. And if we recall that relationship, the POH is equal to the negative log, and I'll write that down. So number 2, POH, the power of hydroxide ions in solution, is equal to the negative logarithmic function of the concentration of hydroxide ions. But because we want to solve for this concentration, we want to bring all of the other variables or terms or functions to the other side. We want to isolate for this. So to bring this logarithmic function to the other side, remember it is to the base 10. So to bring it to the other side, we would get 10 to the power, So exponent of negative, because that just didn't disappear, POH. So 10 to the power of negative POH is equal to the concentration of hydroxide ions. So the concentration is equal to 10 to the power of negative 2.2. We can plug this in to our expression because hydroxide concentration is equal to X. So I'll write that over here. We can go back to our expression to solve for base dissociation constant. X times X is X squared. So I'm going to put 10 to the power of negative 2.2 square divided by 0.1 minus 10 to the power of negative 2.2. Our KB is equal to 4.24917 times 10 to the power negative 4, but we need to adhere to the correct amount of significant figures. So if we look over here in the given question, we are given 3 sig digs, but it's always based on the least certain. And because we use concentration, it is going to be one significant digit. So KB is equal to 4 times 10 to the power of negative 4. For the second question, it asks for pH now. Given that the concentration of hydrazine is 0.500 mole per liter, and the base dissociation constant is given at 1.7 times 10 to the power of negative 6. We know that this is going to be a weak base because a Kb value is given. And remember, this hydrazine is also listed on the constants table. Any value, any dissociation constant value listed there that's not very large and actually has a numerical value constitutes as a weak acid or base. Because we know it is a weak base now, it will interact with water, where the water by default will act as the acid. The base will accept the proton, and therefore you will get hydroxide ions. We can put in our known values. In this case, it is the concentration of hydrazine in the initial setting. Because no product is given, the concentration can be 0, whereas water, we don't never write it because of the liquid state. We account for the changes. It is 1 to 1 to 1 to 1, so it's all negative or plus X. We take the equilibrium by adding the sum of the two rows. When it comes to the Kb expression, we can set it such that the products are divided by the reactants, where the concentration of hydroxide ions are equal to X. We plug in the values that we do know, which is the Kb. We need to solve for X because the only way to get to pH is the OH. Nothing else will get us there. So we really want to find that X value. So we need to solve for X. We can simplify the lower term by using that 100 rule. You can also find it using quadratic formula. We want to simplify the hydrazine concentration. So we're going to compare the hydrazine initial concentration, which can be found in your ICE table, and divide it by the K value. We get the answer of about 200,000. So that's going to be greater than 1,000. Therefore, we can simplify it by taking out that X variable there in that term. So your equation or expression becomes this right over here. We isolate for X by multiplying 0.5 by that Kb value and square rooting it. We get a value of 9.2195 times 10 to the power negative 4. And remember, that's the concentration of hydroxide. We want to find pH. So the only way to find that pH is to go through the steps of converting concentration to power of hydroxide. From there, you can find pH by taking the sum of the POH and pH equals to 14. So the first step here, to get to pOH, you have to use this formula here. pOH is equal to the negative log of your concentration. Plug in the values, put this into your calculator, you get a pOH of 3.035. You're going to take that value and subtract that from 14. So 14 minus 3.035. And you get a pH of 10.96. Now I have to go back to the question to adhere to the correct significant digits. We have 2 here as our least certain, so we're just going to round it to a pH of 11.